Exponential word problems, extreme. Okay, let's read through this. As you read through this, you'll realize we're dealing with an exponential situation, hence the name of the lesson, but also a percentage here. So, foundation of your house has several termites. The number of termites increases at a rate of about 2.4% per day. Let's start writing some stuff down. I know the rate is 2.4%, and that happens every day. We'll move the decimal 2 places to the left. That's the same as dividing by 100. Let me get that. How long will it take the population of termites to double? Well, how long is a question of time, and I want it to double. Now, I do see the word double here, which makes my mind go towards this whole growth and decay factor thing, but that's not it, because they did give me a percent. But here's the deal. I don't know P, and I don't know A, and we're dealing with this formula right here. So A equals P, 1 plus or minus R to the T. And the tricky part about it is they did not give us the original amount or the amount that we ended up with, but they didn't have to. They really didn't have to. Pick any number in the world you want. Pick like a random number. You can roll some dice. I'm going to. And get a number for P. So let's do that. Here goes. Dice here. I'm going to roll my 30-sided die, and we're going to figure out how many termites. You can do this for a math problem? Yes, you can. Oh, there it went. 14. We started with 14 termites. I made that up, but that's okay. All right, but here's the fun part. It doesn't matter what you roll as long as you double it. We now have 28 termites. Okay, so we're going to just use those numbers. Doesn't matter what you start with as long as you double it. You'll see where this is going. 1 plus, because it's increasing, 1 plus 0.024. That's to the T. And I would love to divide by 14, and I will, but when I do, I get 2. So again, doesn't matter. I could have rolled a 29, and then over here I'd have a 58, and I'd still divide and get a 2. Okay? 1.024 here, because we're going to add those. And now we're ready for a logarithm. So log 1.024. There we go. 1.024. 2. Log base 1.024 of 2 is 22.226. Let's see what we're dealing with. How long will it take the population? That is a matter of time, and it is per day. So final answer is 29.226 days. It will take that long for the population of termites to double. Okay, number 2. In 1966, a boy in Miami smuggled 3 giant African land snails into the country. Don't do that. It's just a bad idea. His grandmother eventually released them into the garden, and in 7 years, there were approximately 18,000 of them. I'm not making this up, by the way. Assuming the snail population, I wish I was making this up. Assuming the snail population grows exponentially, write an expression for the population P in terms of the number of years T since their release. Now, very first time I taught this lesson, I was looking at this problem and I'm like, P, that's the original amount, but now it's going to be the amount after time has elapsed. So if you want to change the variable for this, you can. When I did this, I used Y instead, and I wrote this instead of P. I wrote it as a Y. I'm going to just say, well, Y equals A, B to the X, but instead of Y, I'm going to call it P for population after time has elapsed. So I know I'm kind of blending some of the variables we've dealt with because you're dealing with original amount, the principal, or population. You could call it that too, original population. But this is the population after time has elapsed, and I'm using it in a different formula, and it's okay. It's totally okay. And the number of years is T, so instead of X, I'm going to use T. All right, so we're just rewriting the same idea. So here's the equation, but here's the equation with the variables they're giving us. So I also want to determine how many snails there were in the year 1982. So let's jump in and figure some things out. 1966, the boy in Miami, 3. Ooh, the original amount, which in this case is lowercase a, is 3. His grandmother originally released him in the garden. 7 years, so time is 7. There were approximately 18,000 of them, so the population ended up being 18,000. And here's the thing. I just now identified A, T, and P. A, T, and P. I don't know B, so let's figure that out. Now, if you're like, well, what about 1982? Don't worry about 1982. It was in the past. We'll deal with 1982 later. We'll deal with the past in the future. In the meantime, let's figure out what B is, because I can't get to 1982 unless I know what the B value is. So 18,000 equals 3 times B to the 7. Okay, it's about to get a little tricky, but we're going to solve this thing for B. So let's divide by 3. Okay, so that's going to give me 6,000 equals B to the 7. And if you're like, let's use a log. Well, no, because I would use a log if I'm solving for a variable in the exponent, but it's not in the exponent right now. It's just a 7. So my next best guess is to take the 7th root of 6,000, and that's going to be B. So let's take the 7th root, and I'm going to do it this way. 7th root of 6,000, and I get this crazy, ridiculous number. I'm going to use 3 decimal places, and it is 3.465, and that's equal to B. Now, as I actually figure out what happened in 1982, I probably won't use this, probably use that, okay? So here goes. Write an expression for the population P in terms of the number of years T since their release. So I actually haven't done that yet, but I'm just about to. So here was all the work that led to where we're going. It says an expression. I am going to write P equals 3 times 3.465 to the T. So any given year after 1966, I can predict how many snails there are. Now, it's not going to be realistic. Otherwise, these snails would take over the world. Like, you plug in a number, I think it's up, if you go into the 1990s, like if you go like 96, like 30 years after that, then like snails have conquered the whole land. It's just not worth it, you know. But up to a point, it's going to be somewhat accurate. But this is the expression. It is technically an equation, but P is equal to that expression. Okay, that answers the first part where it says write an expression. Now, determine how many snails there were in 1982. Okay, cool, we'll do that. So P equals, don't do this. Don't. 3.465 to the, don't write this, 1982. No. I don't want 1982. I want the number of years since 1966, okay? If you're in 1982, how many years was it since 1966? Think. Don't grab a calculator. And now there we go. Okay. It has been 16 years since 1966. If we're in the year 1982, that's where that comes from. Okay, we're about to find out how many snails there were. Her poor garden. I'm sure they got messed up. Whoo! 1, 2, 9, 5, 3. This can't be right. Actually, we're gonna do it again. 3 times this number right here to the 16. That's gonna change it a little bit. It's gonna make it a little more accurate and higher. Of course, approximately 18,000. We've already rounded before we even really started. There are 1.3, if you want to round it to that point, 1.3 billion giant African land snails. Okay, so have you ever crossed the border into the country and they say, do you have any food with you, or any, like, other than snacks? Like, you have a bag of Cheetos, but like, do you have any food or animals or anything to declare, like anything in your luggage? This is why. It's for situations like this, for real. Like, if you have a rabid Tasmanian devil in your briefcase, they need to know. All right, let's do number 3. And it's going to be kind of fun. The isotope yttrium-90. All right, pause right here. Chemistry lesson. Isotopes are elements that have a different number than normal of neutrons in their nucleus. So like a yttrium atom doesn't normally have 90 neutrons, but this one does. Okay, and they're generally radioactive, which means they decay over time, and you're like, hey, where'd my yttrium-90 go? Oh, it's floating around. The isotope yttrium-90, why 90? Why not 90? Haha, bad joke. Has a half-life of 64 hours. This is going to get a little tricky here. You initially had 465 grams of yttrium-90, Write an equation that represents the amount remaining in grams, where T represents the number of hours. Determine how many grams there will be after 120 hours. Okay, you read it, you realize they never gave me a percentage. So we are messing with this formula, y equals AB to the x. And y meaning y, not yttrium-90, although it is going to represent that. This is going to be the quantity of yttrium-90. The number 90 will not pop up in this, by the way. So let's keep reading again. You have a half-life of 64 hours. Hold that thought. That one's going to be tricky. You initially had, okay, that sounds like the original population to me, or the original amount, 465 grams. Write an equation that determines the amount remaining in grams, where T represents the number of hours. So I would like to rewrite this as AB to the T. I'm going to just use the variables they want. And again, the lowercase y represents the quantity of yttrium-90 after time has elapsed. And we also have this last sentence to deal with, about 120 hours, but we're not quite there yet because I need to figure out some stuff. Okay, so here's the fun thing. A half-life really means the amount that remains after, that half of it remains after a certain amount of time. So I'm going to change this a little bit, and that is my decay factor. We talked about this. This is my decay factor. It's 1/2. But the fact that I'm dealing with 64 hours is going to change this. So I'm going to go ahead and change the structure of this, and that means that every 64 hours I'm going to lose half of it. So we're going to divide by 64. So the exponent, let's write it a little bit better. The exponent is not just t, the exponent is t over 64. Ah, interesting. Yes, it is, isn't it? Okay, t over 64. Okay, so here's what that really means, and I'm just going to grab a scrap piece of paper and I'm going to doodle for the sake of explanation. If I started with some random amount, and I'm not going to necessarily start with that. Let's start with an easy amount. Let's start with 100. Excuse me. Grams. And I have half of it remaining every 64 hours. Then after 64 hours, I will have passed through one full time period. So the exponent represents the number of time periods. And so if this situation happens every 64 hours, I can divide by 64 and figure out how many time periods have taken place. So I'll do all this little work. I have 1/2 to the 1. It's a half. Half of 100 is 50. In 64 hours, I have passed through 64 over 64, one time frame to take half of my original amount. All right, just saying. Okay, so we actually have the expression that they want. So write an equation that represents the amount remaining in grams, where T represents the number of hours. Okay, so how much yttrium-90 do I have? Well, I start with 465, and then I take half of it every 64 hours. That's done, but then they also say, determine how many grams there would remain after 120 hours. Well, after 120 hours, how many times have we passed 64 hours? Well, once, 1.875 to be exact, once and then some more. So the amount of yttrium-90 remaining after 120 hours is 120 over 64, which we just did a second ago. And we'll figure out what this is. So when we do that, we're going to find out how much remains. Whoops, we're going to do it correctly. 120 over 64, there we go. We have 126, let's use 3 decimal places, 772 grams of yttrium-90. There we go. That's what remains after 120 hours. So dividing by 64 is going to really make our exponent tell us how many time periods there have been.